All right, hello everyone. Welcome. Let's go ahead and get class started. Just kind of want to start by taking a peek at the calendar because we're getting very close to the end. Want to make sure everybody understands the few things that we have left. Actually, today I'm going to be introducing the final new topic. So after today, there's no more new material. This is the last topic that we're going to cover in this class, which means we're coming up on exam 3. So next week is going to be our third exam. You can see that I've already got next Monday, so 1 week from today, right here, right now, we'll be doing an exam 3 review session. Just like you saw in the previous exams, I have posted practice quiz and some coding problems. Those are already available to you on Canvas. So please, if you want to get a jump on studying for the exam next week, feel free to take a look at those problems. And please come with questions next week during the exam 3 review. Want to point out a couple other things about the schedule just to make sure you understand what's left, at least for this class. There are 2 more assignments. Assignment 8 is due this week, but assignment 9, I'm just trying to give you as much flexibility as possible. It will be on exam 3, right? So I kind of hope that you do try to get it done before the exam, but I wanted to give you as much flexibility as possible. So it's not actually due until the week after the exam. You do have some time to work on it. You also will be able to use late coupons on assignment 9. If you still have late coupons left and you want to use late coupons to turn in assignment 9, the following week I will have office hours, this week and the following week as well, for people who want to turn in assignment 9 using their late coupons. So that is definitely still a thing. Also want to reiterate my message from last time that if you are struggling this time of semester, which is very common, I know, and if a few extra late coupons would help, please let me know, because that is a very easy thing for me to do. Very happy to give you some extra late coupons if it'll help buy you some breathing room on some of these assignments, help make the last few weeks of your semester go a little bit more smoothly. I want to do that for you. I definitely don't like seeing students all stressed out this time of year. Not my favorite thing, so definitely want to try and reduce that stress level as much as humanly possible. Excuse me. We do have 2 studios left. So if you have not missed a single studio this semester, technically you don't have to go to the last 2 remaining studios because you do have 2 studio drops. But I would again like to remind you that Studio 9 very much is over material that will be on exam 3. So I think very much in your interest to come and complete Studio 9. The last studio is actually on the last day of class when assignment 9 is due, and it's not related to the exam at all. So that one I'm a little bit less concerned about you attending. It's just kind of a fun little studio to wrap up the semester. So not quite as vital as Studio 9 is in my opinion, but those are the last 2 studios that you have. And then again, just kind of want to remind everybody that the final exam is coming up on May the 2nd. However, if you get good grades on exam 1, 2, and 3, and you decide to use your exam drop on the final exam, that is fine by me. I don't have a problem with that at all. We are planning to grade the exams on the 20th. Yes, I know that's Easter, but my TAs have assured me that that'll be fine. So hopefully around this week, you'll know what your grade is in the class and can make that decision on whether you want to show up to take the final or not. That is entirely up to you. You can make that choice. You don't have to tell me whether you're coming or not. We'll be ready. If you want to come, take the final. And if you don't want to come take the final, then awesome. That means you must have done pretty well on those first 3 exams. I think that's all I have in terms of scheduling. Oh, yeah, one other note I wanted to make about the schedule. This Monday, the 21st, is the last Monday that we have class that semester. I will not be introducing any new material because we don't have any new material. Also, the exam will be over, right? So not really a whole lot for me to talk about. However, just wanted to let you all know, and I'll remind you of this next week as well. I still will be here on the 21st if you want to turn in assignment 9, if you want to get some help on assignment 9. It's basically office hours on that day in this room. So I will be here, but we're not going to be covering anything new that day, just available for assistance to help people wrap up whatever they need to wrap up for this class. So yeah, just wanted to make sure that you're all aware of the events that are coming up for the last few weeks of the semester. Does anybody have any questions about scheduling or exams or any of that stuff that's coming up that we can talk about right now before we hop into the Module 9 material? Hope you're all doing okay with the last few weeks. Hope you don't have too many things piling up on you over the last few weeks of the semester. Let's go ahead and start talking about some code for today. This is, I hope, a not too tricky module. It's meant to be sort of a lighter module to end up the semester and act as kind of a bridge, kind of a transition between this class and what the next recommended class would be in the computer science track if you choose to take that class. I know a lot of you may consider this to be your one and only comp sci class, and that's fine, I understand. But for many of you who are computer science majors or minors or just want to learn more about comp sci, the next class, at least the next really big important class after this one to consider taking, is data structures, which is currently called CSE131, but I guess next fall will be called 2407 because all the workday stuff that's going on. But the data structures class is like the heart of computer science, in my opinion. It is really what kind of takes everything that you've learned in this class and steps it up another level. Every program that I write, every program that other programmers write, one of the first things we think about is what kind of data structure do we need to store the data that this program is going to rely on. So the form that your data takes has a huge effect on how you work with that data, the code that you write to manipulate that data. So understanding the different kinds of data structures that exist in the world and how to apply those different data structures to different sets of data is what 247 is kind of all about. So you'll take a look at a lot of different data structures under the hood to kind of see how they work and how they tie all things all together. I'm not going to get that deep into it today. My goal for today is to introduce you to a couple of well-known, couple of very popular, very commonly used data structures, and kind of give you some basics on how to use those data structures. I'm teaching you how to drive the car today, right? And then when you take if you take 247, they'll pop open the hood and show you how some of this stuff works under the hood. That's kind of the goal for today. And so the two main data structures that I'm going to focus on are lists and maps. And actually, we've already seen one data structure before today. We've been using it for quite some time. It's a data structure that I'm sure you're all familiar with, way back on the first exam, called an array. So arrays actually are data structures. We give you that one pretty early on just so that we have something that we can use to store data, right? But arrays are not the only ways, not the only tools available at our disposal to store data and manipulate data, but I will actually use that as kind of a basis today, kind of compare and contrast the data structures that I'm going to look at with you today with the arrays, since that's kind of a data structure that we're already somewhat familiar with, that we already know how to use. Now, these data structures, they're so commonly used that they're provided to us, right? So I don't have to say what a list is. I just understand that Java provides something called a list to me, and I am able to use that list in my program as my data structure if that is what I decide is appropriate. So much like we've seen in prior modules and prior units, a lot of the information that I'm going to be referring to today comes directly from the documentation, and the methods that we see available to us are the ones that we're going to be using upon this list object. So it definitely ties very much in with the object-oriented programming stuff that we've been using. In fact, I would argue that's probably the biggest difference between an array and the data structures that we're talking about today. These are very much objects. So objects, not something we were really thinking about or caring about too much when we talked about arrays. Something we care very much about now. The data structures that we are using are actually objects. So the rules that we've been talking about with objects are going to apply to these data structures. So that is a good kind of tool for us to use to review some of those concepts today. Let's start by walking through a simple example just to kind of contrast the difference between an array and a list. So I'm going to make an example, a very simple example. This exercise right here should, I would hope, at this point, be very trivial to you to make an array that stores all of the colors of the rainbow, right? So I'm not going to spend a ton of time doing this, but I'm going to go through it kind of quickly. But since I'm storing colors, probably a string, right? So I'm going to make a string array called rainbow, and this is all review, right? I have to say how big I want this array to be. There are traditionally 7 colors in the rainbow, right? Roy G. Biv is the acronym that everybody uses to help them remember this. And so then once that's done, I can say things like rainbow dot, I'm sorry, not dot, I'm getting a little ahead of myself. Rainbow at position 0 is equal to red, right? Rainbow at position 1 is equal to orange. Rainbow at position 2 is equal to yellow. And you see where I'm going with this, I hope, right? Green, and then, you know, I don't even necessarily need to do all 7 colors. I think you kind of get the point, right? Without me having to do this. And then if I want to actually, you know, do something with this array, we've talked a lot about how we perform array traversals. So I can use a loop to iterate through this array and print out the contents of it, for example. This is nothing new, right? This is all review from not even recently, but like way back towards the beginning of the semester. Just trying to set up an example here so we can contrast this data structure with the one that I would like to discuss with you next. So real quickly before we move on, you can see I made at least half of an array here. Yeah, there's a few more colors that I maybe should have added, but for the sake of time, I'm just going to run it as is and show you that, okay, this very much will take in the value, make the array, take in the values, and, you know, other than the last 3 colors, which I didn't type in yet, we'll happily spit the values back out, right? So this is all, like I said, nothing new. But let's take a look at how this would work using a list, and then kind of talk about why we might want to use a list instead of an array. So in order to change this, to stop it from using an array and make it use a list, we're going to change actually first this line, since this is what's declaring the array. I want to declare a list instead. So I'm going to say a list. And just like we saw with an array, I can't just say a list by itself. I have to say a list of something. So what am I expecting to store inside of this list? I am expecting to store strings, but kind of pay attention to the way that I said that. So when we're using arrays, of course, we see the square bracket notation. That's classic array stuff that we've seen for weeks and weeks and weeks. When we're using the lists and the other kinds of data structures, we don't use that square bracket syntax anymore. We're going to use, these are called angle brackets. That's the official term for them. Angle brackets instead to specify the type of thing that's going to go inside of this list. But otherwise it's doing basically the same, it's basically the same idea. I'm creating a collection of stuff. What's going to be in that collection of stuff? Strings are going to be in that collection of stuff. This name is fine, so I don't have a problem with this variable name. But over here, because this is an object, if I want to create a new one of them, I have to do what? How do I create new objects? How do I create new instances? So word starts with a C. Constructor. We have to call the constructor. So for an array, we didn't call the constructor. It kind of looks like the constructor a little bit because you do see that new keyword there, right? But it doesn't have the parentheses or anything like that. We have to call the constructor. So I'm going to say linked list of, and actually I don't need to put anything in there. This looks a little bit funny. This looks a little bit funny. We have to include the angle brackets. And you'll notice that I didn't put the word string inside of them this time. You don't have to. You actually only have to do that once on the left-hand side. But you can. If you put the word string in here on the right-hand side, it's not going to complain about that. It's actually okay. It's just redundant. It's not necessary. It's a little extra, but you can say it. It's not a problem. These parentheses, though, why are these parentheses here? It looks a little funny to see angle brackets followed by parentheses, but these parentheses exist for a reason. Why? Yeah, in the back. I'm calling a method. The constructor is a method. The constructor is a method. I am calling the constructor, right? So these parentheses represent that fact. I am calling the linked list constructor. Now the reason why it is angry at me is because even though these things do exist and are part of the standard Java library, I have to import them if I want to use them. Eclipse can help you out with this. You can look up how to type out the import statements. I haven't typed an import statement in years. Instead, I usually just hover over the thing that it complains about, and right up at the top it says import linked list. That is actually what I want to do. And when I click on that, it types the import statement for me. And then over here, I need to do the same thing. I need to import list. And be careful, it does offer me a few different options. The one that I want is java.util. So make sure you're selecting the right option if it does provide multiple options to you. Once I've imported those things though, this line of code is now valid. This is now a legitimate line of code. You can see the rest of the stuff is angry because it's still trying to use an array. We need to switch that stuff to use the list. That's what we're going to get to next. But this is how we create a list. Do you notice something missing from this line compared to how we create arrays? When I create a new array, I have to tell it the size. And here I do not. Think about that for a second. That's actually often cited as one of the great reasons to use lists instead of arrays. Unlike arrays, lists start out as having a size of 0 and will automatically grow and shrink when you add things to the list and remove things to the list. Remember, arrays don't do that. If I create an array of size 7, that array has a size of 7 forever, right? So there's no way to really shrink it or make it bigger without making a brand new array that has that size. For lists, that's no longer true, and that's actually a great thing, I think, from a programming perspective, right? Even thinking about this week's assignment, assignment 8, or even last week's assignment, assignment 7, thinking about how to add a student to a class, right? Kind of becomes a lot more trivial if you don't have to worry about which seats are already filled. You can just add it to the end of the list. Boom, done, right? Very simple, very straightforward, very easy. One exercise that I often recommend to people studying for the exam is go rewrite the course class in assignment 7 and take the array of students out and make a list of students instead and see how that affects the code. I think that's a great way to practice for the upcoming exam next week and how to use linked lists on the exam next week. But yeah, that's one of the great things about lists. The other nice things about lists is that actually they kind of do behave like arrays in a lot of other ways. We just have to use them differently. So because this is an object, I'm not going to place a value into it like this. I'm going to call a method upon the instance of the list that I created, just like we've been doing for all of our objects for the last few weeks. Ever since we introduced this idea of objects, we've been calling the constructor to create instances and then calling methods to operate on those instances. So to put something into a list, we can actually refer to the documentation and see that, oh, there's a method called add. So that's really what we want. It automatically is going to add it to the end of the list, so we need to be a little bit careful about that. If we want it to go in a specific spot, though, you can see that there's another version of the add method that says, hey, I want to put this into this specific spot. So we do have the ability to do it both ways, but if we're just focusing on this simple example, these statements become rainbow.add. Oops. That is not what I meant to do. I hit the wrong button. Sorry about that. Rainbow.add with the value that we wish to add inside of parentheses. So if I make that change to this line, you can see that, okay, the computer seems to be somewhat happy about that, right? So I can make that change for all of these lines of code to get that stuff added in properly. Notice that I'm no longer saying exactly what position these values need to go in. I'm using the knowledge that they always get added to the end to ensure that, yeah, they're going to get there in the proper position, right? And so then our last thing that we need to visit, our last thing that we need to take a look at is this loop down here. This is a great loop for traversing an array, and we can also traverse our lists. So that's good news. We can traverse our lists in a very similar way that we traverse our arrays. It's just we no longer access our lists like this. We need to call the appropriate method upon the list object in order to get this information. What is that method called? Well, let's take a look. I actually know what it's called, but we can also take a look and see that, okay, it's called size, not length. So if we're using arrays, they do call it .length. If we're doing lists or other types of data structures that are objects, usually it's going to be called size instead, which I know is a little bit confusing to have those two different names, but also pay attention to the fact that I put parentheses on there because I'm calling a method, right? I'm calling a method called size that tells me how big this list is. And then finally, the last thing is, how do I get stuff out of this, right? How do I get it to tell me what's in this list? We're not using the square brackets anymore. Again, we're using methods. So I have to find the appropriate method to extract information out of this list. And the method that we're going to need to do that is called get. So here we are. There's a method called get where I plug in the index, and other than that, it works very much in a similar way to the square brackets, right? Very similar idea to the square brackets. But the reason why it's different again is because we're dealing with objects now, not an array, but actually an object. So I'm going to say get I. And now I would argue that this code is functionally equivalent to the what I started with up here using the arrays, except I've switched it to use a linked list instead. I can even run this code and show you that fact to show you that it prints out the same kind of stuff when I run it. If my computer will do it. There we go. Yeah. Notice that I don't even get the 3 nulls on the end because the list is not a length of 7. It's actually only a length of 4 in this case, since I only added 4 things to it. So there you can see, visual proof that lists grow and shrink depending on how many items they contain, unlike arrays, which are always whatever size I create them as, right? The good news about lists and arrays is that they do act very similarly. So one thing that we like to think about, there are properties of data structures that we care about. The properties of the data structures are usually what we use to decide what data structures are appropriate to use for a given program. So think about the properties of this data structure. One property that's very important to us is the fact that this stuff is ordered. It's called a list, and the fact that it's called a list implies that there is an order to the items that come on the list. Same thing with arrays. I always start at 0 and count up, 0, 1, 2, 3, 4. Same thing is true for lists. The first index is always going to be 0, and it's going to count up 0, 1, 2, 3, 4, etc., etc. So lists and arrays are both great for storing data that has an order to it. Any data where the order matters, right? Lists or arrays are considered good tools for that job. There are other cases where the order of our data does not matter. And in those situations, we may want to consider using some other types of data structures. I'm actually going to show one to you here in just a little bit. But before I do that, I want to kind of pause and see if anybody has any questions about using these lists. Yes?
So, like I know with arrays, if we did something like when we get I, like in your loop, if we extracted that value from it and we had an extra step and said system.out.print color, and we set color equal to get I. Is that color actually that up, or is it a copy of?
Let me make sure I understand what you're asking. You're asking, something like this, where we have the line, and then we just print this out like this.
Is color actually the element at that thing, or is it a copy of it?
It is actually the element at that thing, yes. Okay. Yeah, the question was, if I do this, am I making a copy of this color, or am I actually accessing the specific element that is in the list? And the answer is that it is actually the same one that is in the list. So if I make a change to this, and then I check the contents of the list again, I would expect to see changes to the list. Yeah.
Is that the same for arrays?
If you're storing objects in the array, then yes. Things get a little bit trickier when you talk about what we call primitive types like ints and doubles. Those you're more likely to get a copy and not the actual thing. But you're kind of hitting on a topic that is on my agenda for later on today. Because checking objects is different than checking ints and doubles when it comes to that kind of thing. So you're hitting on a very important point. Yeah. Any other questions about lists? Yeah, in the back.
Yeah, I know that we have that whole list of methods that work on lists. How much of that would we be expected to
Okay, so if you're talking about like the exam next week, which is I assume maybe what you're referring to, I'll cover this again on Monday, but I will typically provide you abbreviated versions of this documentation on the exam. I provide a reference page on the back of the exam, and I don't put all of them on there. I'll be honest with you, there are some things on here that I have never used before in my whole life, right? Like, so you don't necessarily need all this stuff. You do need the important ones, so I'll definitely put, add and get on there and some other important ones that we've talked about in class. But you will have this as a reference page on the back of the exam. And the same thing is true for the other data structure that I'm about to talk about as well. Yeah. Any other questions about lists versus arrays before we hop over to that other data structure that I want to talk to you about? All right. Cool. So honestly, in my experience, right, if I get to data that is ordered in particular, so ordered data is what we're talking about right now, using a linked list is honestly generally my preference over an array. I actually think that these are more convenient than arrays, mostly for the reasons that I talked about. They can grow and shrink. If you know for a fact that I need 7 things and I'm always going to have exactly 7 things and it's never going to be 8 things or 6 things or any other number but 7 things, using an array is actually still a very appropriate tool to use. But I would say most programmers would probably prefer not to use arrays and would prefer to use lists when they need to store data of that type. So I would encourage you to maybe revisit some of your past assignments that use arrays and consider using, swapping them out for lists. Another common use for arrays is 2-dimensional data. So you'll notice that I didn't really talk about 2-dimensional lists, and that's because not really a thing. You can kind of do it, sort of. I'm not going to do it. I'm certainly not going to expect you to know it for an exam or anything like that. So for 2-dimensional data that's in a grid, arrays are actually still a really good tool for that purpose. Lists can be used, but have their limitations in that regard. The other data structure. So actually, I want to point out one thing here. There's a unit called sets. That is not a data structure that I really want to talk to you about today. We have covered this one in the past. I left this information in mostly just so you can take a look at it. But I want to be 100% clear right now that you will not be asked about sets on exam 3. I'm not going to cover sets in detail in class, so I'm not going to expect you to know it for the exam. This is mostly just here for your reference. However, this idea of a set of information also appears in the data structure that I do want to talk to you about, which is a map. So in order to understand what a map is, we're going to, again, compare it to the data structures we already know. Lists and arrays both care about ordered data. I made a big deal about that. That's not true anymore with maps. Maps do not care about the order of the data. In fact, one of the properties about maps is that they are unordered, meaning that regardless of what order I put things into the map, it doesn't record that information. It does not care about what order I put things in. There is no order to the data at all. It is just sort of an amorphous blob. The same thing's true for sets, actually. Sets are unordered. Sets also do not allow duplicates, which is another property that we care about with data structures. Do I want to allow the same value to appear more than once? Arrays very much allow us to do this. I can put the same word, right? If I wanted to go back to my prior example and just make all of these values say red, right? It wouldn't care. It would happily put red in there as many times as I wanted to. Same thing for an array. I can make an array that has red in every single spot if I wanted to. Sets, that's not true. I put the word red into a set. If I try to put the word red into a set again, it says, it's already here, so I'm going to ignore it. That kind of behavior is also something that we kind of care about with maps. The way that maps store data is very differently than arrays and lists. So we're no longer dealing with 0, 1, 2, 3, 4 on up to however many elements we have. I kind of think of maps as create your own index. So with arrays and lists, the index is sort of defined for us. Start at 0, count up by ones. With maps, we get to say what the index is. What do I want the index to be? And actually, we don't call it the index anymore for that reason. The data that is in maps is stored in what is called key value pairs, where the key is kind of the index, right? And the value is the value that is stored at that index. But now, instead of just our keys being 0, 1, 2, 3, etc., they can be literally anything. They don't even have to be numbers. They don't even have to be numbers. So let's take a look at the phone book example. This is kind of a classic example of using a map where, okay, here's where we actually say the structure of our map. I'm saying, notice there's two types here, right? There's two types here. This is the type of the keys. So I'm saying that the keys are going to be strings. I'm not going to use 0, 1, 2, 3, 4. I'm trying to represent a phone book. So actually the keys are going to be someone's name, right? I want to know the phone number for Professor Shook. So if I type Professor Shook in, plug that into my map, I want it to spit my phone number back out, right? That's how phone books work. So here the key isn't a number, but it's somebody's name. Somebody's, it's a string value, but the value, you'll see the phone number itself is in fact listed as an integer. I actually think there's an argument to be made to call that a string as well, but I didn't. I used an integer here. Notice this is very similar to the list example. We're calling the hash map constructor, right? So I'm calling the constructor to make this object, for this data structure. And before we talk about how to use this, I want to take a look and see, some information about the map in terms of what it looks like when talking about maps, or if you're familiar with Python programming, as I know at least some of you are through past conversations. Maps in Python would be referred to as dictionaries. That's another name that means the same thing as a map, at least as far as I'm concerned. Curly braces are often what you'll see used to refer to maps or dictionaries. And so after we create this map, all we've done is call the map constructor. You can see it's empty. I have an empty map. I have no keys. I have no values. I have nothing. It is a completely empty map, right? But take a look at some of the other methods. There's that size method again. So if I say, hey, how big is this map? It tells me 0. You haven't put anything into the map yet. And then I'm asking to look up the number for Ghostbusters. So if I go to this empty map and I say, hey, tell me what the phone number for Ghostbusters is. Well, remember, it's empty. It doesn't know what the phone number for Ghostbusters is. There's nothing in this map that represents that. So it's going to tell me that it doesn't know. And the way that it tells me that is by saying null. It's a very, very important thing to keep in mind. If I try to retrieve a value from a map and it's not there, the map is going to tell me null. That's something we need to be very careful about, right? Because I think some of you have already seen what can happen if you have a null value and you try to use it to do something, right? You get the dreaded null pointer exception, which means that you can't call a method on nothing. You have to have an instance first and call it upon that. So you do have to be a little bit careful. The map will tell us, I don't know, if it doesn't know. And the way it does that is by saying null. But let's take a look at some more practical examples. Let's put some stuff into the map. So for lists, we use an add method. But that's not how we get stuff into maps. For maps, we use a method called put. And when we call the put method, we have to give it a key value pair. So the type of this thing has to match what I've told it the types of the keys are going to be. And the type of this thing has to match what I've told it the types of the values are going to be. So when I run this statement, I'm effectively saying, put an entry into this map so that if somebody looks up Ghostbusters in the phone book, it tells them that this is the phone number. I'm making that association, right, between the key and the value. You'll often hear that referred to as an association between the key and the value. And so if we look at what this map looks like after putting in that very first phone number, you see here's what that map looks like when we print it out. I've just printed out the map directly and I can see, oh, okay, it tells me that Ghostbusters has this value associated with it. There's a size of 1, and now when I say go get the phone number for Ghostbusters, it happily tells me what the phone number for Ghostbusters is. That's good, right? So I can put stuff into the map and I can get stuff out of the map. Those are your two primary methods for interacting with maps. Yes?
Can you do it the other way around? If you like put in phone book.get and then the number, would you get Ghostbusters?
You cannot. No, it has to be in this order. The type of the first has to match this, and the type of the second thing has to match this. It is a one-way association, in other words. The key is associated with the value, not the other way around, right? The arrow is pointing from key to value in my mental picture of the map. There is no arrow pointing back from the value to the key. Yeah. And think about also what that means. I can't plug, 55555 into the map and get Ghostbusters back out. You actually can get that representation if you really want to, but it takes a lot more work to get it. And not really how maps are intended to be used. They're meant to be that one direction, like I said. But if we return to the example that we've been talking about, we're going to put some more stuff in. So I'm putting in, the famous number from the song, and then here's another number for Saul Goodman. But notice, actually, Saul Goodman somehow happens to have the same number as the Ghostbusters do. Is that a problem? How is the map going to react to this information? Well, let's scroll down a little bit and see. You can see that after we put in, Jenny and Saul Goodman, that the map looks like this. And the map very, very happily accepted the same phone number for two different people. Does not care. Does not care. So this kind of touches on something that I mentioned earlier. Whether we can store duplicate values or not is something that we care about. And actually, we can have duplicate values in a map. That is very possible. But what about duplicate keys? Could I have the Ghostbusters appear more than once with multiple phone numbers? Right? That's another question that I think is worth considering. And so let's try that. Let's try to put in another entry. So Ghostbusters is already in there, already in the map with all fives. I'm saying put the Ghostbusters in there again with this number, so it's different this time. It's not the same phone number. What's going to happen? Is Ghostbusters going to show up twice? Well, let's take a look and see what happens after. Oh, actually, we need to write a line of code to pull that off because the exercise ends here. So let's do that. Let's write a line of code to just print out the map after we put this second entry for Ghostbusters into the map. Do we expect to see Ghostbusters appear twice now, or what's going to happen? Well, let's run the code and find out. Scroll down to the very bottom. You can see that okay, this is what our map looks like, and Ghostbusters only appears once. And notice that the old value for Ghostbusters is gone, right? It has been replaced with the new value that I put in. So can I see the same value show up? Yes. Can I see the same key show up more than once? No. No, I cannot. Maps do not allow for duplicate keys. They do allow for duplicate values, but the keys can only appear one. I can only have one entry for Ghostbusters. It's not possible for me to have multiple entries for the same key. Also, I mentioned too that maps are unordered, and this is good proof of that. Consider that the very first number I put in was Ghostbusters, but when I print out the map, you'll see that it shows me this one first. That was actually the last number that I put in. So you can see that it is not keeping track of the order that I add these things to the map at all, right? It's pure key value pairs. Yes?
So are you just going to print it out in a random order?
I'm sorry?
Is the order that it's printed out just random?
You can essentially assume that it is random. I believe that it is consistent, meaning that if I print out this map and then I print it out again, it's not going to give me a different order the second time. It'll always give me the same order every time I print it out, but it's not the same order that I add them. So I can't assume that it is in any particular order at all. Could be anything. Yeah. And that kind of goes back to the important part of programming, the important part of learning about these data structures is knowing when to use certain data structures. If order matters to me, then map's not the right tool for the job, right? I need a list. That is very much the way that a programmer would think about solving a problem. This data is ordered. That's list all day. I need a list. Don't need a map. Would not be appropriate. You can also iterate through maps, and that's what this file is for, is to show you how you can iterate through maps. It is a little bit tricky. You have to use a for each loop. You cannot use the other style of loop for I equals 0, I less than, map dot size, because for the same reasons I've been talking about. There is no index 0, right? That loop works because arrays start at index 0, and lists also start at index 0. But maps don't even have indices. They have keys. And that key could be anything. It's not, I guess it could be 0, but it certainly doesn't have to be. Could be literally anything. So if you're going to write a loop to iterate through a map, this is how I would do it, where I'm actually iterating through the keys of the map, and then I am using the get method to pull out the values, to extract the values from the map. For the purposes of the exam, though, what do I want you to know regarding maps? And you're going to get practice with this in the studio this week as well. Studio 9 is going to have you do a map example. The main things that I'm concerned about with maps are the put and the get method, right? Obviously, how to create a map, but then also how do I put things into the map and how do I get things out of the map? Understanding the key value pairs and not the 0, 1, 2, 3 index like we've seen with other data structures. Those are the big takeaways. There are other things about maps that I could talk to you about, but that's the big stuff. That's the stuff that I really care about regarding maps. I've got one more example to work through with you today, but before I do, does anybody have any questions about this map example? Okay, so we're going to wrap up with one final example today, and it actually doesn't have to do with data structures, but well, kind of does, kind of doesn't, but has more to do actually with this idea of equality. So equality is an interesting idea when dealing with integers, for example, and checking equality using double equals. Can very easily say, 2 is equal to 2, right? They mean the same thing. There's no other real way to express this concept of 2. It just is, right? So comparing the equality of numbers, very straightforward. But comparing the equality for objects, now these are more complex than just a single digit, right? Objects contain instance variables, and so it gets to be a little bit more confusing in terms of what it means for two objects to be equal to each other. As it turns out, there's two different ways that we use to check for equality between objects, but they mean two slightly different things. So the one way that we've seen to check equality before today, and we've been using almost exclusively before today, is double equals. And double equals can still be used to check the equality of objects. But the equality that's being checked with double equals is a different kind of equality than you might actually expect. So when checking something with double equals, I am asking the question, is the thing on the left-hand side of the equal sign literally the exact same thing as the right-hand side of the equal sign? I don't want it to be a carbon copy, right? I want it to be literally the exact same thing. And you might be wondering to yourself, what distinction I'm trying to make is. Let's go through this example, and I'll try and illustrate that with some code. I'm going to go through the person example, and a few weeks ago I actually showed you how I kind of represent objects in my mental model. I want to do that again with this example. I think it's very important, and another very, 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 very big hint. You're going to see a problem that seems pretty similar to this on the exam next week, right? So definitely a good one to pay attention to and make sure you kind of understand how it works. So in this example, we're talking about people, and the instance variables for people, they have a name and they have an ID number. Very arbitrary, right? Excuse me, not worried too much about any of the other information that we could represent, just having some instance variables to help us keep track of different objects. And so this is kind of review, but a very important review that I want to go through with you. I'm calling the constructor here. I'm creating a new person. When I look at this line, right, my mental model says, okay, the new keyword is here. That means that I'm actually creating a new person object, and to kind of review, that means that I'm going to put a new circle This is the actual instance. This is the actual person that I'm creating. And inside of that instance, I usually represent that by typing out, name is, what was it, John Smith. And ID is 1, right? So that takes care of the right-hand side. Anytime I see new, whatever, new call the constructor, that tells me that I'm going to create a new instance. I'm going to draw the new object, and I'm going to fill in the instance variables inside of that object. The right-hand side of the equal sign, this is a variable declaration, but we're talking about objects here. So what this is really, P1 is what I would describe as a reference or a pointer, right? Pointing to a particular object. And the way that I represent that on my diagrams is by literally drawing an arrow, right, to that object and labeling it P1. So the right-hand side of this equal sign actually is represented by the circle. The left-hand side of this equal sign is represented by the arrow with the variable name, right? There are two different things that are kind of going on here. And actually the next line does exactly the same thing. You'll notice that, like we've seen before, or like we've talked about before, it's possible for two people to have the same name. Happens all the time, right? But that's kind of why ID numbers exist, so that if I do have two John Smiths, I can distinguish them by having two different ID numbers associated with those two different John Smiths, right? So this would be represented the very same way. I'll try and run through this real quickly so we can get to the important part of this example with the, the arrow pointing to it, and then the P2 as the variable name, and then inside of here the name would still be John Smith, right? And the ID this time would be 2. All right, let's get back to this idea of equality. The first thing that we're going to do is we're going to check equality, and we're going to do it not using double equals. Remember, we're dealing with objects now, so this is actually calling a method called equals. And the way that the equals method works is by comparing the instance variables. So if I'm checking for equality using dot equals, I am going to compare the instance variables of the two things that I'm checking for equality. And if those instance variables match, right, then I'm going to say, yes, those are in fact equal to each other. This can be used to, this is the doppelganger check, basically. This will check to see if you have twins, right? If you have a carbon copy. Not just one object, but two objects that have the same instance variables. That is going to be a true equality statement in terms of dot equals. So whenever you come across a dot equals statement, you're going to look at the values for P1. See, all right, the name, yeah, that does match, right? The name for P2, but the ID doesn't. The ID doesn't. And because these two instance variables do not match, dot equals is going to be false. In fact, if you run this code, we'll see very much so that this first equality statement is going to come back false. They are not equivalent, right? They are not equivalent. But let's talk about this line of code right here. This is perhaps a deceptively simple line of code. We are not creating an instance of an object here. Do you understand why that is the case? I don't see the word new. I don't see a call to a constructor, right? It doesn't say person parentheses. So if I'm thinking about my mental model, how my diagram looks, right? I'm not going to add any more circles. There's no more circles being created here. So what is this line of code doing? It's creating a new reference. Creating a new pointer. The way that this statement is going to update our diagram, well, P2 already exists, right? P2 is right here. This is saying create a new reference to the same thing as P2, and I want that to be called P3. So now I have two labels. I have two names pointing to the same instance. Everybody with me? I would make the argument that we as humans do this all the time. All the time. You all know me as Professor Shook, right? Or something along those lines. When I go home, my 6-year-old daughter does not call me Professor Shook, right? She calls me Dad. Professor Shook, Dad. 2 references that point to the exact same instance, right? We as human beings use this concept all the time. Very common for us to do. The question then that we're kind of asking, right? If I'm talking not about dot equals, but now double equals, I'm saying, is Professor Shook Dad? Right? And for my 6-year-old daughter at home, I would look at the references, right? Professor Shook, Dad, yeah, absolutely pointing at the same thing. But for anybody, sitting out here in that room, that's not true, right? I'm not your dad. Not that I'm aware of, anyway. So that would be false. Professor Shook points to me, and Dad points to wherever the heck your dad is. I don't know, right? So not here, not in this room, at this moment in time. So that's a different form of equality. I'm not asking, do they look the same? I'm asking, are they the same? Are they actually the same thing? Or another way of thinking about what double equals is doing, at least in terms of objects. If I say this thing double equals this thing, and the answer is true, then the thing on the left and the thing on the right are the same thing. Like quite literally the same thing, right? There's only one object. If double equals returns true, there's only one instance being referred to. Both things are referring to the same instance. There's only one instance there. If dot equals is true, it could actually only be one instance. So I want to make it clear, right? If I say, P2 dot equals P3, which I think is even on this example, that says go look at the instance variables. And oh, hey, surprise, surprise, the instance variables for P2 and P3 are the same because P2 and P3 are the same. So that's another important thing to kind of keep in mind. If double equals is true for 2 things, then dot equals guaranteed to be true, right? Has to be. Doesn't work. Doesn't make sense otherwise. But if dot equals is true, we can't say that double equals is also going to be true. It could just be a doppelganger. It could just be a twin, an identical twin, right? So dot equals is being used to check for identical twins, and double equals is being used to answer this question. Do these 2 labels actually point to the same? Is Dad Professor Shook, right? Do those 2 labels point to the same thing? So if we return back to the code, we can see, yeah, P3 dot equals P2 dot equals P3, absolutely true. But the reason why is because the instance variables being compared are the same. The reason why P2 dot equals P3 is true is because P2 examines the ID and sees a value of 2, and then P3 also examines the ID and sees a value of 2. That's why dot equals is true. Dot equals checks the values of the instance variables to determine equality. If we take a look at double equals, like on line 50 here, double equals is asking, do both of these arrows point at the same circle? If the answer is yes, then double equals is true. If the answer is no, then the double equals is false. And so those 2 forms of equality are useful in different situations. Sometimes I don't care if I'm talking about the exact same object. Sometimes I just want to know if they're functionally equivalent, right? Doppelganger, if they look the same. Other times I do care. Is this the actual object that I am looking for? Is this the specific instance of the thing that I am looking for, right? Double equals is the right tool for that job. And so to kind of wrap up this example, here you see I actually do create, right? I create another instance because I am calling the constructor. So on the exam, if you get asked a question like this, anytime you see that new keyword, calling the constructor, I want your brain to think, oh, I got to add a circle to my diagram, right? Got to add a circle. Anytime you see something like this on the left-hand side of the equal sign, that's telling you to add a reference, add an arrow. And so here we would say, here's my circle, here's my arrow, and they're trying to be a little clever on this example because even though even though the name and ID are equivalent to this object over here, it's actually two separate objects, right? So then consider, to kind of tie all things together, if I use dot equals to compare P4 to P3, I'm looking at the instance variables. So P4 has the same values for the instance variables as P3 does, right? But P3 double equals P4 doesn't look at the instance variables. It looks at where the arrows are pointing, and because they're pointing to two different objects, if we look at P3 is equal to P4 or P2 equal to P4, we'll see that that is in fact false. P2 and P3 both point to a different instance than P4 does, even though the instance variables look the same. Dot equals is true, double equals is false. I have an identical twin, right? It's the case of an identical twin. Cool. Any questions about that example? All right. If there aren't any questions, that's it. That's all the material I have for you. The new material in this class is coming to an end, so you just need to study the material I've already given to you. I'll stick around if you have questions about the homework assignment or anything I've talked about today. But otherwise, I hope you enjoy the rest of your day, and I'll see you in the labs on Wednesday. Thanks, everyone.